Give me a second. Oh, okay, so can everyone hear me?
Yes.
Okay. So today we're going to be finishing up a shape, and then we're going to go on to polygons. So the last time we were here, we stopped with the Rhombi, and we're going to start with a quick proof of the Rhombi property. So we're going to get right into it, and I want you guys to go ahead and try to prove that every rhombus is a parallelogram. Just think about your parallelogram properties here. Yeah, and remember that every rhombus has 4 equal sides. All right, so does anyone need more time? Okay, so I'm going to go over the solution, and it's actually quite simple. And basically, we already know that a parallelogram, if we basically know that if you have okay, so we know that something is a parallelogram if it has two, if opposite sides are equal. That's a property we learned, right? And this a rhombus obviously satisfies its opposite sides are equal, even though they're all equal. And even if you didn't do this, a quick way would be just to draw a line here, and you realize that SSS, all of these are congruent, so this angle, corresponding angles must be congruent as well. And therefore, this is a parallelogram because you have two sets of parallel lines. So I'm going to go on to the next one. So now we have a little bit, it's a bit more meaty. We're going to have a little bit more information. So I'm going to give you guys this problem. So basically, I want you guys to go ahead and try this out. If you're stuck, you can message me or Taylor, or just put it in chat.
All right, can everybody see the question now? Alright, you should be able to see both the diagram and the question now.
Okay, so I'm going to go over the first part. And just like before, if you remember your properties of parallelogram, you can prove the first part pretty easily. So we already know that we have a rhombus, so all sides are congruent, right? And because of this, we know this is a parallelogram because opposite sides are equal. And you want to prove that essentially this diagram is true. And how we can do that is, so pretend that this is our rhombus, right? So we know since in a parallelogram, diagonals must bisect each other. So in every parallelogram, you must have this. And a rhombus is a parallelogram, so therefore you can do this. Yeah. But we also know another property of the rhombus is that all sides are equal in length. Right, so you can do this. Oh my. And now to prove that they're all congruent, well, it's pretty trivial from here. We just have SSS congruence for all of these. So this pretty much just solves letter B. And you see that these angles, all of these angles right here, they're all corresponding, right? They're all between the side length of one tick mark and the side length of two tick marks. So what that means is that all these angles must be equal, and since this whole angle is 360 degrees, you must have 360 divided by 4, it's 90, so therefore these are indeed perpendicular. And now I'm going to give you guys a few minutes to try out C and D. Use this fact that you have right angles and see where that can get you.
And if you have any ideas, feel free to type it in chat.
Okay, so I'm going to label some things. So if you're stuck, look at this diagram. So we know we have a bunch of, AX and XC must be the same, like, because the diagonals bisected. And given AC is 30, so this must be 15. And similarly, since this BD is length 16, this must be 8. And we already proved that this must be a right angle. So I think it should be somewhat obvious from here how to proceed with C and D. So I'm giving you guys about 1 minute to go ahead and try to solve this problem.
So I should have clarified to do private message.
Okay, so I'm going to go ahead and solve this problem here. So we know that every triangle in this, well, every single one of the smaller triangles are all congruent to each other. So they almost have the same area. If you look at AXB, well, it's a right triangle, and you can find the area of a right triangle pretty easily, right? So the area of AXB is 15 times 8 over 2, which is 15 times 4, which is 60. So the area of one triangle is 60, and you have four triangles, so 60 times 4 is 240. And that's the area of our whole parallelogram. But what about AB? Well, one very powerful tool we have is the Pythagorean theorem, and we have a right angle, so that's pretty much what we're going to use. So, if we let AB be x, then x squared should be equal to 15 squared plus 8. Now, if you know your squares, or you could just multiply this out, it's equal to 225 plus 64. And this is equal to 289. So luckily for us, this is a square. I believe it is 17 squared. Yeah. And now we're just given x squared is equal to 17 squared. So x is equal to 17. So this is it's pretty interesting from just using properties of parallelograms. Just from the diagonal length, we were able to get the side length. And that's actually property restricted to rhombuses. Like you can't do that for every parallelogram. And you see here that it is indeed 240. And here, just a quick summary of rhombi. We have all rhombi are parallelograms, and this is because opposite sides are parallel. But notice that the opposite isn't true. You can't say that all parallelograms are rhombi because you're not guaranteed to have all sides be the same length. And similarly, we already proved this, but the diagonals of a rhombus are perpendicular. And finally, the area of a rhombus is half the product of its diagonals. And you can prove that it's the area of this rhombus is half the product of the diagonals by breaking it down to right triangles. And then you could pretty much do what we did for C, and you could find a general form for a rhombus, and you'd find that it is half the product of the diagonal. So I'm going to give this over to Caleb, and Caleb, do you want to go ahead and teach some stuff about squares?
All right.
Okay.
All right, let me turn on annotation. All right, so we just studied quadrilaterals with that have all equal sides. We've also studied rectangles, which have all angles are equal. So when we have a quadrilateral where both the angles and the sides are all equal, we get a square, shown right here. And they're one of the easiest quadrilaterals to work with because you can apply everything that we've learned about quadrilaterals. Parallelograms, rectangles, and rhombi, all those properties, they're all going to apply here. So I'm first going to ask you guys to find the perimeter and area of a square if the side lengths are 9. Should be pretty simple. I'm just going to give you guys like a minute or so. And go ahead and private message if you have the answer. All right, I see plenty of correct answers, and it is pretty simple. We know that all the sides of the square are equal already, so it's going to be 4 sides times 9 units, so that's just 36 for the perimeter. And the square is considered a rectangle, so the area is just going to be the length times the width. And these dimensions are going to be the same because it's a square. So it's going to be 9 squared. And that's also why we call it the square of a number. And this will give us 81. Now this time, we're going to give you guys a diagonal. So again, find the perimeter area, but this time you're given that the diagonal has length 8.
Caleb, do you want to make it so everyone can private message everyone so people can message
Yeah,
me
I'm
there?
trying to figure out where that's located in settings. I mean, for now, I guess you can just private message me. I'll give about another 30 seconds or so. If you think you have the answer, go ahead and private message. All right, I'm gonna go over it now, the solution. So we know that squares are rectangles, and we learned before that rectangles have diagonals that are congruent. Squares are also rhombi, so the area is going to be half the product of the diagonals. Um, so it's just going to be 8 squared divided by 2, which is 32. And side length, we can find that because the diagonal of a square splits a square into 2 45, 45, 90 triangles. So each side is just going to be the diagonal divided by the square root of 2. So we have 8 over square root of 2, which can be simplified to 4 root 2. And we also find it, since the area of the square is the side length, we can just take the square root of the area. So if we just take the square root of 32, we get 4 root 2. And since that's the side length, we just multiply it by 4 to find the perimeter. So we get 16 root 2. And so here's a little bit of a summary on squares. Given that S is the side length of a square, P is the perimeter, A is the area, and Z is the diagonal, we have the perimeter is going equal to 4 times the side length. The area is going to be the side length squared. Diagonal is going to be side length times root 2. Perimeter is going to be diagonal times 2 root 2. And the area is going to be diagonal squared over 2. And these are all just found from properties of the other quadrilaterals we've learned about already. And that's why squares are quite easy, but they're also quite useful. They'll show up a lot in problems, especially with circles, because both involve segments of equal length. And you might see some of these in the following problems. And I'm going to hand it over to Sahil for these practice problems.
Okay, can everyone see my screen?
You're good. Oh, wait, my head's gone.
Okay.
And
So, okay, we're going to be going over some contest problems. So these are going to be a little bit more tough than the previous problems. So I'll start with this one right here. And basically you're told that the middle square, the one that's touching the bigger square at 4 points, has area of 4, and then the bigger square has an area of 5, and you're given that the square breaks down one side length into B and A, and you want to find the product of A and B. If you have any ideas, post them in the chat. Oh yeah, I also believe you guys can PM me and Caleb both. So if you have the answer, go ahead and shoot us a PM. Does anyone need more time? Okay, I'm going to give you a few hints, and you might be struggling to relate A and B somehow, or these. You might want to try and look for it from an area approach, like you want to relate these triangles somehow to the bigger triangle. And one thing I would tell you to do is look at these angles and see how you could relate this triangle, and the same reasoning applies to all other triangles. This is if you're going for an area approach, but there is an algebraic approach as well. So we're going to give you guys about like 1.5 minutes to go ahead and try to solve this. Okay, so I'm going to go ahead and go over the solution. So the way you can relate these two triangles is, it might be like just looking at the diagram, it might be obvious, but these are in fact the same triangle. And the reason why is because let's say this angle is x, right? Then we know that this angle has to be 90 minus x, right? And since this is a square, this must be a 90-degree angle. And we know 90 minus x plus 90 plus whatever this angle is must be equal to 180, right? So we know this angle right here must be x, because 90 minus x plus x is equal to 90, and you add 90 plus the right angle, it's 180. So this triangle must in fact have an angle of x. So this means that this triangle and this triangle have two angles that are equal. So you have a similarity, but you also know that they share the hypotenuse, because a square has all equal sides, right? So the hypotenuse must be equal, and then therefore you can use ASA, and these two triangles are in fact the same. So what that tells us is, let me just clean this up a bit. What that tells us is that this must be of side length B, and this must have side length A if you like match the corresponding sides. And we already know that a triangle's area is 1/2 the side lengths, the product of the lengths, right? So area of one of these triangles is AB over 2. So the area of all the four triangles must be AB over 2.
Hello?
Yeah, can you guys hear me?
Yeah, it's just that I came late, a little late. Can you explain to me what you guys were doing?
Go over the handout when we email it out after the meeting.
Yeah.
Thank you.
So the reason why we're doing this, by the way, is because we're going from an area approach. We're given a lot of areas, and it's like pushing us to do something with area. So now we know the area of the triangle is 2AB, and we know the area of the bigger square is 5, right? So the area of the smaller square must be 5 minus the area of the triangles. So that's the area of the smaller square, which is 4. And therefore, you have AB is equal to 2. AB is equal to 1/2 if you solve it. And there is another approach to this, but for the sake of time, I won't go over it just yet or in this lesson. So we're going to go up to the next problem. And here you can read the algebraic solution if you want. So here you go.
This one's trickier, but I think you guys can figure it out.
What was the answer of the last one again?
Last answer was C, 1/2.
Okay, so some people are having some confusions over what the question is asking. So let me just clarify. So anything that isn't white in this diagram. So that basically means this, anything that is not white, you're looking for the area of anything not white. The circle shaded area.
You're looking for the ratio of the circle, the light gray. So it'd be like this area, and this area.
Yeah, you're looking for red over blue. Basically.
Yeah, that light gray, light shading over total shading.
Yeah, let me just clean up this diagram. Okay, so a hint is that you might be like, oh, there's so many like areas you have to find. But my hint would be to try to get some side lengths because you have right triangles and you have squares and you have circles. If you have side length of any of those, you can easily find the other ones because they are all are like.
Another hint is that they give you that the circle's radius is 1. So you know that this is 1.
Yeah. Okay, so I'm gonna start to go over the steps. So it's important in this problem to be organized because you have like 3 different types of areas you could, find. So let's go ahead and have a clear goal in mind. So let's just try to find the area of the white square. So, well, we know since the radius is 1, the diameter must be 2 in total, right? So you could use the formula for the area of a square in terms of its diagonal. In this case, like if you remember, the area of a square is d squared over 2, which would be, well, the diameter is 2, so it's 2 squared over 2, which is 2. Or you could just, if you don't remember that, or you're too lazy to write that formula, you could just realize, oh, this is just 4 right triangles, right? And then each triangle has area of 1/2, so 1/2 times 4 equals to 2. So now we know the area of the square equal to 2. Okay, but what about so from right here, you could easily find the area of the circle because you're given the radius and the big square. Because now you know that the side length of the big square is going to be 2, right? From this diagram, it is pretty clear that the big square has a side length of 2. So the area of the big square should be 4. Okay, now we're getting somewhere. But it seems like for now, let's try to get the area of the circle. That seems like a good plan, right? So the area of the circle, well, we already know that the formula for the area of the circle is pi, let me write it down, r squared, pi r squared, right? And we know the radius of this circle is 1, so the area of the circle is just equal to pi, right? Now, this is good. Now we have 3 areas. So let's see what the question is asking. So now we need to find the ratio of the circle's shaded area. So how are we going to find the shaded area? Well, we're trying to basically find this area right here. And you might realize, okay, well, this is just 1/4 the area of the circle because, like, I think it's clear from this diagram that since all these are right triangles, this is 90 degrees, and in the circle there's 360 degrees. So this must be 1/4 of the circle. So if I'm trying to find the area of this whole section right here, let me change to a different color. The area of this whole section is just going to be pi, the area of the circle divided by 2. Oh, is it?
I think you hit undo on the annotations.
Is there not a reverse undo?
I don't know.
Okay, well luckily I remember stuff. Okay. Let me write important stuff again. So the area of this square is going to be equal to 2, and the shaded square is equal to 4. The area of the circle is equal to pi. And if we're just looking for this section blocked off, this is just pi over 4 because this is 1/4. So the area of this is equal to pi over 4. And in order to find this little shaded area right here, you can subtract this triangle, right? And the area of the triangle is 1/2. So therefore, the area of this shaded region we want, so pretend that's the shaded region, is going to be pi over 4 minus 1/2, right? And the shaded region, you can just multiply that by 4, right? Because there's 4 of these. So if you multiply by 4, you get the area of the total shaded circle's shaded area. So if you multiply this by 4, you're given that this, what we want, so the circle shaded area, is going to be equal to pi minus 2. We just multiplied this by 4. And now find the area between the two squares. Well, that's just the area of the big square minus the small square. And we already know from our areas that this is just 2. So this is over 2. The area between the two big squares is 2. And now, well, we know pi is about 3.14, so this is about 1 over 2, and that is our answer. That might seem like a lot of work, and with my messy work, it might have seemed like that, but all you have to do is just remember to stay organized, and if you know your areas of your shapes, this is just a multi-step problem that boils down to simple steps. So there is our answer. And now we're going to go off with one final practice problem. And here is your image, because this is quite hard to figure out. So go ahead and try to give this a shot.
It's probably the hardest problem out of those 3. But apply what you've learned. Oh, by the way, you're trying to find basically the area of this square we've already pre-drawn for you. So you probably want to find the dimensions for the area.
So the little hint is that, well, you might see there's a bunch of similar triangles here. And while it is possible to solve these similar triangles, there is a much faster way to do this.
Yeah, I've highlighted the square.
Okay, I'm going to go ahead and start in the solution. So we want to find the area of the one that Caleb highlighted blue. And a good way to do this is to try and break this square um into easier parts that you can deal with. So obviously this middle part is a square. Oh my. Oh my. Okay, wait. Luckily we didn't draw much there. So you can see pretty easily that the area of this middle square is going to be, well, this side is length 1, 1. So this must be side length. This must have a side length of 3. Therefore, the middle square must have an area of 3 squared equal to 9. Now, if you look at these four red triangles, you can easily prove that these are all congruent because A, they have right angle, and B, they share their hypotenuse. And you can angle chase, and you can find that these do in fact have like the angles are in fact equal, so you can use ASA. And from here, it's actually quite simple because the area of a triangle is just based on height, and we already know the height of this red rectangle, 1, and we know this side length, it's 3, right? Because 1, 1, 3. Therefore, the area of one triangle, 3/2. Well, we can just multiply this by 4 to find the area of all the red triangles, and we get 6. And, well, would you look at that? Well, we found the area of the middle part and that red triangle, so this gives us 15. Add them up, and that's our answer. Any questions here? Okay. So the answer was indeed 15. For the sake of time, we're not going to go over this review sheet, but I really recommend this because I know you might mess up a lot of the properties, or you might forget what is the hierarchy? Is a rhombus a parallelogram a rhombus? So I really recommend you guys to go through this on your own, but we're not going to be messing around with quadrilaterals for the rest of this lesson. So this is really good. So review this. I really recommend everyone to review this.
Yeah, we will be sending the handout out, so please go through this part. This is a summary of all the quadrilaterals we've covered.
Yeah.
Very useful
So,
information.
and here's some good general tips when you're trying to solve a problem with quadrilaterals. And as I said, we're not going to be dealing with quadrilaterals for the rest of this lesson. So we're going to start on polygons. So I'm going to give this over to Caleb. Caleb, do you want to start on polygons?
Sure. One step. All right, let me pull it up. All right, so we're gonna give a quick overview because the meeting's about to end on polygons, and we'll do some more on polygons next week. So right now we've only covered shapes that have 3 and 4 sides, rectangles and triangles and quadrilaterals. So shapes that have more than 4 sides, they exist, like pentagons. And in general, they're called polygons. And that'd be like any shape that's closed and they have line segment boundaries. They don't have to be regular. They can look really odd, like this one here. But they can't be open. So this would not be a polygon. And here we have basically a list of the number of sides and the polygon name. The points where the polygons meet. Okay, no, we do not come back when the meeting ends. We're putting less than 15 minutes because that's what most people voted. The points where the sides meet are called vertices, and they form these interior angles. So this would be on the inside, and on the contrary, it's like this would be an exterior angle, the ones on the outside. And any line segment drawn through vertices that aren't adjacent would be considered a diagonal. So if I drew this, that would be considered a diagonal. And these would be the names of the polygons. I wouldn't advise memorizing them. That is something useful to know. And any polygon where the sides are equal in length and the angles are equal, they're called regular polygons. So that'd be something like equilateral triangles and squares. So that's just a basic introduction to polygons. And see you guys next week, because this meeting's going to end in a couple seconds probably.
Yeah, and
Please do review the handout.
yeah, and
we'll
to
be
say
covering
is that we added a pretty good P set this time with solutions. So go ahead and try to do that. There's some challenging problems in there, but I think you guys are capable of doing them. And well, I think we don't have much time left. And so with that, I hope everyone's having a great summer break. And Caleb, do you wanna?
Yep, I'm gonna end the meeting now.
Okay. Thank you guys for all joining.
See ya.
Yeah.